3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
We got a roll program.
The Saturn V rocket is one of the most amazing vehicles ever created by humans. And if you could have one person explain the Saturn V to you, who would it be? Today on Smarter Every Day, we're in the middle of a series about going back to the moon. We looked at how the Apollo astronauts trained to go back to the moon on something called the Lunar Lander Test Vehicle. We even spoke to one of the original engineers over that program. We also looked at one of NASA's early ventures into autonomously landing on the moon, something called the Mighty Eagle. We also took our first look at the Saturn V. We got to meet an engineer named Luke Talley. He was one of the original IBM engineers over what's called the instrument unit. This is the large computer shaped like a ring up near the top of the rocket that steered the rocket towards the moon. Now it's time to go deeper and understand the entire Saturn V rocket. Wernher von Braun said, "As the IU goes, so goes Saturn." That right there is none other than Luke Talley. So there is no better person to explain to us how the Saturn V works than Luke. He understands how all three phases of this rocket works because the IU has to control the entire rocket. Today we're going to talk to Luke Talley in great detail, but before we do that, I want to tell you a little bit more about the person that Luke Talley is, because that will influence how you feel when you're receiving this information. November 10th, 1944, a young sailor from Alabama is killed in the Pacific Theater in World War II, and this young sailor had a 3-year-old boy and a wife back home in Alabama. This little boy turned out to be extremely curious, and like most little boys of the time, he loved making crystal radios and things like that, but he couldn't afford kits like this because they were kind of bootstrap and everything, didn't have a lot of money. So a lot of people in the community helped him put together things like this, just different parts. You could make your own crystal radios and stuff like that, and that's what he did. And it became clear that this young boy had an aptitude for electronics, which is why Luke was able to use his dad's GI Bill, because his dad couldn't use it, and Luke went to the University of Alabama to study electrical engineering. I want to show you this picture. This is Luke and his wife Kitty. This is Luke's favorite picture in the entire world. This is them all decked up and she's sitting there on the hood of the 57 Chevy. This is a really cool picture because Luke and Kitty got married shortly after this photo, and he studied electrical engineering at the University of Alabama, and that's what started his career. After that, he went to IBM, where Luke quite literally became an award-winning engineer on the Apollo program. This is a plaque that was used at IBM as a part of the instrument unit team. You can see that it's signed by Alan Shepard, hailing Luke as a pretty important person. This is part of the Manned Spaceflight Awareness Coordination effort there, where they would make the employees that were working on the hardware know more about what was going on. Luke solved a really big problem. There was a problem on one of the early Apollo missions where a coax melted because it got hit by the sun on its way to the moon, and Luke and his fellow engineer here, they solved this problem, and Luke was awarded an award. This is the result of that. He got to go see the launch of Apollo 13, and you can see this right here is where he was given that award. They were talking about all the things he did and the fact that he was invited to attend the launch of Apollo 13 at Cape Kennedy on April 11th. This book, which is one of Luke's most prized possessions, I can't believe he let me borrow it, has all kinds of things. You can see pictures of Luke and his wife attending the launch, all sorts of stuff like this. They have different meet and greets with astronauts at that launch. So you can see Luke Talley is not just a normal engineer. He is an award-winning Apollo engineer. I thought this was cool. You could see the name tags there. Really, really interesting. And perhaps one of my favorite photos is this one right here. You can see Luke and his young bride, Kitty. You can see them at the launch pad for Apollo 13. What I think is so amazing here is you can see on the side, if you look really, really close, it says April 1970. That's amazing. So as you can see, Luke Talley is the perfect person to teach us about the Saturn V. He's seen one launch, And what's even more impressive to me is that the instrument unit that he worked on had to touch every single component of the rocket that had some type of pyro detonator, a rocket that had to cut on. They had to program everything. So they had to know exactly when it needed to fire. So for those reasons, I'm excited to introduce you once again to Luke Talley, who is going to teach us about the Saturn V. Let's go get smarter every day. We're going to meet Luke here at the U.S. Space and Rocket Center early one morning before the museum opened, and one thing you'll notice is Luke's ability to recall facts and numbers is astounding because he actually lived this. He moves pretty fast, so try to keep up, but what we're going to do is we're going to start at the first stage, then move to the second stage, then the third stage, and then we're going to talk about the launch escape system. Along the way, we'll talk about some other things, but here we go. Let's learn about the Saturn V from Luke Talley.
I call this This is the mouth-dropping entrance of the Saturn Hall. And you come in here and you see these, each of these about 12 feet in diameter. Each of these engines now produce 1.5 million pounds of thrust each. The 4 outer engines are gimbaled. That is, they can move. They're controlled by the computer up in the instrument unit, which is on top of the third stage. During the flight, the first stage will go through the speed of sound at about 60 seconds. Shortly after that, you get the maximum aerodynamic pressure on this vehicle, and it is like 2 giant hands have it, shaking it for all it's worth. Each of the engines can move anywhere in a 5-degree circle. As we go through the speed of sound and we get maximum aerodynamic pressure, we would see them move about 1.5 degrees. That's the most we ever saw them move. Most of the time, except in that high vibration period, they would move at maybe 0.5 degree.
And that was actually pointing the rocket.
Yes, and that steers the rocket. So you move these 4 outer engines as you need to steer the rocket. When you move the engine, you not only move the rocket, but you cause it to flex. These engines are so powerful that there are points in the flight where if you move this engine too quick, you can break it in two. Break the rocket in two, not the engine.
Oh, wow. And what are these engines? What are they called?
Okay, these are called F1. I have no idea why it's F1. That's just the number, okay? The thing that to me is just incredible is each one of these engines now, the fuel is kerosene and liquid oxygen, of course, the oxidizer. This thing burns a ton of kerosene and 2 tons of liquid oxygen every second, each engine.
That's because when you say, man, this does a ton of whatever,
That's right.
you're doing hyperbole, but you're literally saying a ton of kerosene
That's
a second.
right. Per engine. So these 5 engines are burning 15 tons of propellant every second. So the mass of this thing changes very rapidly, and that affects these bending modes. So we had to measure that kind of stuff and program it into the computer system so that we knew not to.
So you're saying each of these engines can move?
Each of the 4 outer engines can move. The center engine's fixed. It doesn't move. So
How do they move? Do they have pistons?
they have actuators.
Will you show me?
Can you see this pointer?
Yeah, a little bit.
Okay.
So that thing right there is an
The
actuator?
engine has an actuator. There's an actuator here, and then there's another one up on the other side of it up there. So there's 2 actuators per engine. The actuator is a hydraulic actuator, servo mechanism under control of the computer in the instrument unit, and they're using the kerosene as their hydraulic fluid. There's plenty of pressure in the tank, so I don't need a pump. So I'm saving weight and complexity and so forth. And they look at it and you say, you sure we saved any complexity? But that's true.
Oh, so there's like a lot of aerodynamic or airspace systems have a hydraulic fluid.
Oh, you have a hydraulic fluid. Well,
And
the
you don't
upper stages have to have the hydraulic fluid, but this thing, we just use the kerosene.
Interesting. And that saves a whole set of piping.
A whole more set of piping, complexity, affects your reliability. Number one concern is reliability in this thing. You want to have it as perfect as you can because there's 5 million parts or something like that in this thing. So every part, if it's 0.9 times, I got 5 million of them, and then well, that ain't real good. So I need 0.999. So I got to have 99.999 something % chance of making the mission in order for all this stuff to work that has to. So that's one of the main issues. Now the engine itself, as you look at the engine, can you look up there?
I can barely see your laser, but you're pointing in this area right here.
Okay, so we have the thrust chamber, and then we have a nozzle extension on the back. But the interesting part of this engine is all this that's mounted up above the thrust chamber. Okay, this is a jet engine to drive the pumps to get 3 tons of propellant through that engine every second. So this is a jet turbine in here, and this jet turbine is about a 50-some-odd thousand horsepower turbine. The helicopters that fly around Huntsville probably 5,000 to 7,000 horsepower engine. So this is a monster turbine. Probably one of the more interesting points of it is the thrust chamber itself. The throat temperature is 5,900 degrees. Okay?
It melts stuff.
That will melt any of these materials. So what they do is, if you can see this, it has fine tubes running down this thrust chamber region here. The kerosene, before it's burned, is actually routed down these tubes. Okay, it comes down a set of tubes, goes back up another set of tubes, then in the engine to burn it. And the flow of that in the wall is how you're cooling that engine to keep it from melting.
Now the oxygen was liquid oxygen, right? Was the kerosene super cold or just...
No, it's just plain old liquid kerosene.
Okay. You throw all that down in here into the combustion chamber.
Yep.
And what does that look like? That mixer plate there.
Yeah, the injector plate is just a large diameter plate, has about 6,000 holes in it. Some of the holes are squirting kerosene, some of the holes are squirting liquid oxygen.
Do we have something here in the museum that shows it? Yeah, so we can see that?
Yep.
Interesting. And so you said the 4 on the outside would gimbal.
That's right.
But the one in the middle does not.
No.
So how do you, with the computer, how would you know which ones to control? Could you
Well, your
spin?
guidance, you have a guidance platform in the instrument unit, and it's telling you where you are, and you have a stored profile of where you want to be. So 25 times a second, he's reading the guidance platform and calculating, or part of the calculation, for where am I versus where should I be. Based on that, he determines which engines need to be gimbaled in order to steer you in the right direction. Do I need pitch? Do I need yaw? Do I need roll? Do I need all the above? And all of that's done in the...
And it's a closed loop system?
Yeah.
That's amazing.
The thrust chamber up there where we're talking about the little tubes, that's all made out of a metal called Inconel. Nickel, cobalt, chromium, very corrosion resistant. This sucker's burning 2 tons of oxygen every second. So if it's a piece of iron, it would melt, it would rust in a heartbeat. Okay?
Really?
So they had Inconel blankets. The engines, they had just blankets on the engine, they had blankets on the base. The problem you have with this thing, once you get up a little out of the atmosphere, that center engine gets extremely hot from all the heat coming off of these. So you're trying to keep as much heat as you can away from that center engine.
Oh, interesting, because you're kind of in a low pressure zone back
Right.
here.
Oh, yeah.
Yeah, because you're moving forward and you got this little pocket.
That's right.
Interesting. So
Everything is blanketed with an insulating blanket to try to keep all the heat in the engines instead of dumping it over on that poor center engine.
interesting. I didn't know that. That's amazing.
As we say in South Alabama, he's hotter than a $2 pistol.
I like that song too. That's amazing.
So in here, as you look at this thing, you see there are parts on here that are yellow. Anything in here that's yellow is ground handling equipment. So you see those plates are there, and that's so this thing won't sag as it's laying on its side. So once you get it up, stand on the pad, you would remove the yellow pieces. And we'll see a lot more of that on the forward section.
And that's the original design for the hardware?
Yeah.
Okay.
Yeah.
All right. Following you.
Okay, so the first stage will burn 2.5 minutes, takes them up to about 40 miles high and 5,000 miles an hour. Now, at that altitude, you're pretty high, 40 miles up. Well, he's still climbing as he's at separation. So when things separates, you think each of these engines back here is 9 tons. So we got 45 tons of engines. They attach to a cross member of aluminum that's another about 20 tons. So we got 60, 70 tons of stuff. So you would think the rocket is climbing, he would do this and fall. But he's going 5,000 miles an hour. When it separates from the second stage, it does sort of tilt down, but this thing will go almost 70 miles high before it finally starts coming down. Falling from 70 miles, when it hits the Atlantic, pieces just go everywhere.
Kablooey?
Yeah, kablooey. That's a good
And
way
to be
put it.
clear, the reason you separate the rocket is you've got all this extra mass.
Right. Trying to get rid of everything you've used.
Once you're out of
right.
all that fuel.
Sitting on the pad, we're about 6.5 million pounds. The first stage is like over 4 million pounds of that. Okay. The first stage is a big chunk, but it gets you up and gets you up through the atmosphere and on your way up to 5,000 miles an hour. So as you walk up beneath the thing, you'll see there's smooth sections and corrugated sections. The smooth section directly above where I'm standing right now has the USA on it, is the fuel tank. Okay, so that's where the kerosene is. This thing is made out of aluminum plate, inch to inch and 3/4 thickness. They form a flat plate. They mill the inner surface for strength and some slosh baffling, and then they put this thing in a giant press and bend it. Well, this plate is 1/3 of the circumference. Then they take these plates, stand them up, and they have this automated welder. As I recall, there was something like 20 to 30 passes to weld this 1.5 inch, 1/4 thick aluminum plate. I remember some of the mechanical guys talking about it. They would set the thing up, they would put up these what we call test coupon, just a piece of aluminum to check out the weld to make sure that it's okay. So they make the welds, then they take this thing, slice it up, put it on the microscope, and they said you would be hard pressed in most cases to tell the virgin aluminum from the weld. It was very, very precise.
So they were super skilled craftsmen.
Yes, yes. The forces from the engines are transmitted out through this structure we was talking about, and all the forces are transmitted upward through the skin. There's no internal beams or anything like that. So all your forces are going through the skin. Well, the tank now has to withstand the upward force plus the pressure in the tank, called a hoop stress.
Yes.
Okay. So the tank area has to withstand more forces than do the inner tank areas. So the inner tank areas are made with this corrugated material, so I can use a lot lighter weight material because I'm only having to withstand upward force. I don't have any inside pressure.
Oh, so, well, correct me if I'm wrong on this, Luke. So right there, I'm looking at the corrugated stuff.
Right.
It has a bigger cross section so that it can withstand more axial forces.
Well, it's just corrugated to give it more strength.
So it's not going to buckle.
Right.
And
Yep.
So are there tanks inside? Like, am I looking? So this is a model. I don't know if this is a correct model.
Yeah, this is a pretty good little model. If you look, the fuel tank is the lower section down here, and if you look inside the tank, you can see that the liquid oxygen lines actually run through the fuel tank. Those things are about 18 inches in diameter, and if you had to bring them out around the tank, you would mess up your streamlining on your rocket, on your surface. So they're actually going through it. Now, the problem you have here is liquid oxygen would freeze the kerosene, so the piping that's going through there is kind of like a big thermos bottle.
Okay, so you're saying like this is the liquid
That's
oxygen.
the oxygen tank.
So the oxygen sat above the
Above the
kerosene.
fuel, yep.
And these pipes that go in between
Right.
the two.
Yep.
You've got these big pipes that go. They sure do. How many are there? Is there one
5,
for
one
there's
for each engine.
Just a direct line.
Yep.
Okay, and so you want to make sure that you don't have frozen kerosene around that. So is double walled, or how do they do it?
Yeah, it has an inner wall, outer wall, and then it has a low pressure gas in between, just like a thermos bottle.
Really? And the purpose of the low pressure gas is to insulate.
Insulation.
Wow. Okay. So volumetrically, how does the chemistry work? Do you have more fuel or more oxygen?
Oxygen.
More oxygen.
Yep.
So how does that?
Well, you look up here, you about a 2 to 1.
Where does the oxygen start?
Oxygen tank is in the smooth section up top up here.
Okay.
The one right above us was the fuel tank. This now is the oxygen tank. You can see there's about a 2 to 1.
2 to 1. Okay. Wow. So
And density is about the same.
is it? Okay.
Oxygen is like 9 pounds per gallon. Kerosene is like 7, I think.
Really? So we're still under stage 1.
We're still on the first stage. We were talking about the injector plate. Down in the throat of the engine is this injector plate, got something like 5,000 holes or something like that. And some of the holes are spraying kerosene, some are spraying liquid oxygen. And you have these baffles. When this engine was first made, the Air Force started development of this engine early on. They thought that nuclear weapons were going to be much heavier than they turned out being. So they thought they were going to need a heavy lift rocket. They thought they were going to put manned orbiting laboratories, spy in the sky type things, and ultimately the technology got ahead of them. So this engine was transferred to NASA to resolve the final issues and use it on the Saturn. Originally it did not have the baffles. The problem is this stuff spraying in here starts a circular rotating motion, so this gas starts circulating in this giant, like we're talking about stuff swirling around maybe 2,000 RPM. I mean, it's really moving in there. Problem you get with that is these injectors, sometimes they mix, sometimes they don't mix well, so you wind up, you can get an engine that I'm getting too much oxygen in an area and not enough kerosene. It turns into a settling torch and cuts the end off of the bell.
Really?
And then the other problem you have is if I get too much kerosene and not enough oxygen in this thing, it starts like a car that's running rough on the road. So now it starts this terrible vibration, it'll shake it to pieces. So the baffles break that swirling motion up into much smaller areas that then don't have such a major effect on it. Once they put the baffles in, and this is only happening in the first few inches of the injector. So first few inches into the engine off of the injector.
Mm-hmm.
So these baffles were enough to solve the problem.
Several injector designs, such as this LOX dispersion injector, have been tested in an effort to increase combustion stability margins. Other designs tested include the baffled divergent ring injector, low fuel delta P injector, 21 compartment baffled injector, and the divergent ring injector.
So basically what they're doing is they're controlling they're controlling a very huge turbulence problem.
That's right.
They're cutting it into smaller chunks, and then that way you can get more complete mixing in these sections.
That's right. Yep.
Are these the pipes you were talking about here?
Yeah.
So these
are
are
the tubes, the Inconel tubes where you're pumping the coolant. Now this big baffle around this thing, we take the jet turbine. There's a nozzle extension on the engine, which is not on this one laying on its side. Another 6-7 feet of engine out here that's a nozzle extension. Well, it's made out of high-strength stainless. And what they actually do is they take the turbine exhaust. The turbine now is running a fuel-rich mixture. So its exhaust temperature is only about 1,200 degrees. So by capturing that exhaust and routing it around here and then injecting it into the walls of this nozzle extension and then having little openings around the interior of the extension, the flow of that exhaust in the walls is how you're cooling the nozzle extension. Kind of hard to think of cooling with 800 degrees, but it's better than 5,000.
wow.
And then you allow the exhaust to be injected into the nozzle, and that way your extra thrust you're getting out of that is put in the direction you're going. That thing will produce about 18 to 20,000 pounds of thrust. So if you squirt it out to the side, you'd forever be correcting with another
Just the
thrust.
cooling section is 18,000 pounds of
Just the exhaust from the
Oh, I see.
turbine. Yeah.
So you have to control where
That's
your
right.
coolant
So you
goes.
direct it into the thrust chamber so it's going in the direction you're going. Okay,
Luke, you're absolutely right. We could do this forever, couldn't we?
that's right. I don't know how you're going to cut this, but
Oh,
it'll be
man.
fun.
That's
All right.
quite the reveal for stage 2.
We'll hustle.
This episode of Smarter Every Day is sponsored by Brilliant. Brilliant is a fun way to learn about all the stuff I love. Science, technology, engineering, math. It's super convenient. You can do it on your computer or right on your phone. And there's thousands of lessons with exclusive new lessons added monthly. One of the things that I like about Brilliant is they have a daily challenge. You know what? Let's just do this daily challenge here. Oh, okay. This challenge is about figuring out how many positions are needed to cover an entire area, because you've got a convex thing in there. Incorrect. 3? Show me how to do that, Brilliant. Oh, okay, I wouldn't have put the guard down low. Daily challenge is just so smart. Yeah, it doesn't take a lot of time. You will enjoy it. Yeah, get smarter every day. I challenge you. I challenge you to get smarter every day by doing the daily challenge. Recently found an old college notebook of mine from when I was taking calculus. I was just trying to get the right answer for a test, it looks like. Brilliant's different. It's more about understanding, and you don't have to pay 4-year college tuition level money. It's literally free. The way my brain works, it's like cause and effect. If I can change something and see how it changes the system, that helps me understand better. And I feel like whoever made these little modules really understands that. The cool thing about the offer here is you can just sign up for free. You can do that at brilliant.org/smartereveryday. And the first 200 of you, if you'd like to get the annual premium subscription, you can do that. And it's 20% off. Big thanks to Brilliant for supporting Smarter Every Day, and thank you to you for supporting the sponsor.
Okay, now, when we get to the top of this stage, we were talking about ground handling equipment. You see this big yellow structure on the top of it. This is how you lift this thing off of the transporter and pick it up and put it on the launch pad. Then you would remove this yellow structure up here, and then there's a piece missing that would go from the base of the stage out to about where I'm standing. I think it's 12 or 15 feet, something like that.
So you and your team, whoever controlled the firing and the timing sequences and things like that. So we've lit off the engines, we've burned all of our fuel, and it comes time to do separation. So you have to shut
So you have to shut those engines down.
MECO, main engine cutoff.
That's right. And then there are 4 fins on the base. There's a fairing that flares out so that your engine, when you can gimbal it without the atmosphere streaking by and holding you, keeping you from gimbal. All right. And then in that fairing, there's a fin. All right. There's 4 of them around it. Well, at the base of that fin, pointing in this direction, there are 2 big solid rocket motors. So there's 8 of them around that thing. So this thing is connected to this inner stage with a piece of ordnance. Okay. So the computer says, all right, time to shut it down. Main engine cut off, fires this ordnance. This ordnance now separates. The stages are strapped together with tension straps. Around the interior of those straps is the ordnance. Computer fires the ordnance, severs these, same time fires those retro rockets to slow this thing down. Doesn't back it up, just slows it a little bit. This piece that's missing up here, the inner stage, there are 8 more solid rocket motors around it. And they're fired at the same time to put thrust on the second stage to keep the propellant seated in the tank so I can get these engines started.
Because of slosh.
That's right. You got to get that stuff down in the tank. Otherwise, when you shut off, it just kind of wants to float forward, okay?
Okay.
So you have a little bit of thrust to pull that stuff back and get these engines going. Once you get these engines going, then you jettison this inner stage, and that's to get rid of excess weight.
So there's a lot more going on in stage separation. Okay, so check me here. So engines cut off.
Yep.
And then we blow the tension straps here.
Yep.
And then we have those retro rockets on the fins.
That's right.
Fire those to slow this down.
Right.
And then we have a kick right here.
Then we have these are called ullage rockets.
Oh, okay, so we have a little
push
bit of
forward a little bit.
Yeah, a little kick in the pants.
Seat my tanks, fuel and propellant in the tanks, and then start these engines. Now these engines, first stage, 1.5 million pounds of thrust, F1s. These are J2 engines. The fuel here is liquid hydrogen. So hydrogen gives you a lot more efficiency, but boy, hydrogen's really tough to mess with. 426 below zero, so everything in a whole different world now for messing with a bottle of kerosene versus this stuff, okay? But more efficient. So each of these engines now, the first stage, remember we were burning 3 tons of propellant every second to produce 1.5 million pounds of thrust. These are burning about 600 pounds a second to produce 230,000 pounds of thrust. So these 5 engines equal about one of those first stage engines.
I see, but you have less mass that you're hauling around.
Right. That's right.
And so you don't have to accelerate all that.
Right.
So.
And I'm carrying hydrogen, which is pretty light.
Okay.
Hydrogen density, remember we said liquid oxygen is 9 pounds per gallon, liquid hydrogen is 7/10 of a pound per gallon.
Oh, wow.
Okay, now, the difference there means that these pumps on these poor little engines, they have to work really hard. The pumps that we were spinning, the turbine is spinning the pumps on the first stage engine at about 5,000 revolutions per minute, okay? The oxygen, I believe the oxygen pump on this one is about 8,000 revolutions per second, per minute, and the hydrogen is 37,000 revolutions per minute.
Oh, I see.
They're working hard because hydrogen is the low density. It's got to work very hard to pump a bunch of that.
So volumetrically, you're having to pump a lot faster because you have less mass, but you still need the same amount of, well, you need a lot of mass in order to make the chemistry work.
Yeah, you got to get some oomph out of it. That's technical talk.
That's amazing. So where's that pump?
Again, so there's each engine. Each engine has its own. So we have 5 engines here. 4 outer engines are gimbal, just like the first stage. These, I think, first stage could move 5 degrees. I believe these would operate closer to 10 degrees.
And you're controlling these with your computers
These
as
are
well?
all still under control of the instrument unit. Everything's under control. Everything we've talked about so far is under control of the instrument unit.
Well, how do you connect the computer from, so that means the instrument unit, which is over there.
It's
that
on
big,
top of the third stage.
It's way up there at the top of the third stage. How do you connect the computer?
Yeah, you got cables going down, all the way down.
Where would they be?
They would be going between the stages. In the you won't see them on here.
Okay.
They're on the inner stages. They have disconnects, okay, and then they have a backup guillotine. Quack! Make sure that sucker's cut free.
Really?
I don't want this thing hanging on a cable back here.
So it's
right?
a blade.
Yeah.
Explosive blade.
Yeah. So the stages are all connected through their independent lines from the instrument unit. Now there are not many lines there. You know, there's probably 20 or 30, not too many. Yeah.
That's amazing. And so this engine, what was it called?
J2.
The J2 engine.
Yeah, J2. They'll be on the second stage and the third stage.
So a lot of people spent their entire lives just working on this engine.
Oh yeah, a lot of people spent their entire lives working on one part of that engine.
Really?
It's kind of the way it goes.
And then here you come along and you get to control everything.
That's right. Yeah. Okay. Well, above us is the S2 stage. All right. Now, the S2, we got a little bit of corrugated, but most of it is smooth.
Okay.
All right, so in the first stage, remember we had the hydrogen, we had the kerosene tank, and then we had the liquid oxygen tank, and they're two totally separate tanks. And here we have a deal where there's a common bulkhead between the two tanks. That saves a tremendous amount of length, which saves a tremendous amount of weight.
What is a bulkhead?
I don't have a hemispherical tank here and then another one up here. Actually, I've got one surface, and that surface serves the oxygen tank below and the hydrogen tank above. But they share, one of the bulkheads of the tank is shared, okay? Now this stage you see above us up here, it has sort of a funny looking surface to it. This was a phenolic honeycomb grid, and then it was filled with foam. The hydrogen tank hydrogen is so cold, 426 below zero. You really have to insulate it, and you have to insulate it very, very good. The problem you run into is if you don't insulate that tank, the boil off from it will be so great that you can't fill the tank. So you got to insulate it to fill it, number one. Plus you got to insulate it to make sure it lasts any time. So the second stage is insulated on the outside. This was used on some of the early flights, this phenolic deal. Later on, as my understanding is, they went to like big styrofoam blocks just glued to the outside. It worked a lot better. The upper stage now, the upper stage will last. First stage, we were burning 2 minutes, 2.5 minutes. This one's gonna burn about 6 minutes,
wow.
Okay? So not long into the flight, these two stages are gone. But the third stage now, he's gonna go in orbit, and it's gonna be a number of hours before we're through with it. It's actually insulated on the inside of the tank.
Really?
Okay, now, when you come to the end of the second stage, beginning of the third, we've got another inner stage, and of course it's missing here. So there's a tapered section that goes, the first two stages are 33 feet in diameter. This third stage and the instrument unit are 22 feet in diameter, and the spacecraft is 11 feet in diameter.
Okay.
They knew there were going to be a lot of us Alabama guys working on it, so 33, 22, 11, they were keeping it simple. You don't have to put that in.
Somebody did make a decision though, didn't they?
Okay, so now when we get to the third stage, we've only got one engine.
Okay.
Well, before first two stages, we've got 4 outer engines, and we can gimbal those, and we can make the rocket pitch, we can make it yaw, and we can make it roll. With one engine, I can pitch and I can yaw, but I can't make it roll.
Interesting.
So the two black pods, there's one up here on the upper right, there's one on the left, probably can't see it. There's a set of thrusters in there to give us roll control while the engine's burning.
What's that called? Is that called the reaction?
This is called the Auxiliary Propulsion System, APS.
Okay.
These are hypergolic, nitrogen tetroxide, whatever that other stuff is, hydrazine.
MMA, okay.
Hydrazine. When they squirt it into the chamber, it immediately burns. You don't have to have an igniter. Okay. So during the boost phase, they have The APS gives you the roll control. Now this will go into orbit and will coast, and while we're coasting, there are roll, pitch, and yaw thrusters in there to control it.
And you were controlling those?
And that's all under control of the computer instrument unit, right. First stage shut down at about 40 miles high, and then it went on up higher and then fell into the ocean. Wound up about 450 miles from the Cape in the Atlantic. They put out maritime warnings. You don't want that thing to fall on your boat while you're out there fishing. The second stage now, he shuts down. The first stage was still climbing. This one now, he's up to about 115 miles high, traveling 15,500 miles an hour. He's going to do a nosedive into the atmosphere. Going into the atmosphere probably begins to break up at altitude. Doesn't burn up, just breaks up. And pieces in the neighborhood of 2,000 miles, 2,500 miles from the Cape, something like that out in the Atlantic. Okay, now the third stage is going to burn for about 2 minutes. Okay, now he's going to take them up not much higher, 117 miles higher, probably 17,500 miles an hour, puts them in orbit. Now the problem we have here, or the situation, we're going to the moon, but we launch from the Cape. You can only launch in certain directions from the Cape, all right? So what you do is you launch and you wind up in an orbit about the Earth, but the orbit plane is in a different plane from the plane of the moon that's also orbiting the Earth, all right? So we go into orbit, we shut this thing down, usually coast an orbit and a half. We could have coasted as much as 6 hours before batteries ran out, okay? Usually only an orbit and a half, hour and a half or so, 2 hours. And what we do is when our orbit, we come around in our orbit and it intersects the plane of the moon's orbit, we restart this engine again. So this one burns twice. Now he will burn for about 6 minutes and we'll take them out of the moon's plane, out of his orbit plane and into the moon's orbit plane and up to 24,500 miles an hour. Now they're on their way to the moon. Now after that, the crew's got to get separated and do all their magic, okay? So we'll talk a little bit about that if you want to.
Let's do it. Where do you get rid of the third stage? Does it go to the moon with you?
Oh, we'll get back to that one. That's a good one. Okay, so we won't spend much time on the spacecraft. We'll just say here's where it is.
Yeah. We won't talk much about the little thing that went to the moon, like the actual land part.
If you want to know about that, go to Johnson Space Center. Here's probably the best little thing you can show is this model here shows the third stage, the instrument unit, and the lunar module is inside what's called the Spacecraft Lunar Module Adapter, the SLA, the SLA. And then the service module atop that, and atop that is the command module, and this is where the 3 astronauts are located. Now this launch escape system up here on top of it, if we had to abort during the first stage burn, if we lost 2 engines or the rates got too high, if the rates get too high on that first stage, you can break this thing in two also. So that is an emergency, get them off of there right now. So there's an emergency detection system hardware in the instrument unit. We don't need the computer, we don't need any of this, it's all hardwired. It's triple redundant and everything. So if I lost 2 engines on that first stage, that system would automatically fire a rocket motor that's in that launch escape tower up there. That thing would pull just the command module with the crew and, the crew members are inside, the astronauts are inside there. So this thing now would pull them wherever the abort occurred, would take them 30 to 40,000 feet higher. Then it would jettison and they would come down on their parachutes.
And so I'm looking at it.
That's only in first stage burn.
I'm looking at it right there.
Yep.
So I can see the nozzles on the back side. So that's a rocket.
It's a solid rocket motor, yeah.
And those nozzles are pointed out.
Right. That's right.
And that's to not burn the top of the gumdrop.
Don't melt the spacecraft. Now the spacecraft, during that point, as they're going up, in case you were to have an abort, that launch escape system actually has a cover that is actually over the top of the spacecraft. Until they jettison this during second stage burn, they can't hardly see anything. There's a little window down at the side they can see out, but the main one they can't, it's covered. And that's in case we had to fire that thing, we wouldn't damage the spacecraft. Yeah.
Interesting.
And when the launch escape tower separates, it pulls that conical section with it as part of the.
So when does that fire? I mean, you got to get
During
rid
second stage, just after second stage burn starts.
Okay, so it's after
We jettison it.
So you jettison it while you're firing the second stage?
Yes. Yes.
Really?
Yeah.
Oh, okay. I didn't realize that.
It has a little motor up at the front of it that will pull it away and pitch it up out of the flight path.
So there's a little motor on top of.
Yeah, there's a couple of little extra auxiliary motors inside that thing. That.
Is it a pretty dumb rocket up there? It's solid, right?
Yeah, it's solid. That thing has as much thrust as a Redstone rocket, just doesn't burn as long. It'll snatch them away there real quick. They will pull some G's.
Really?
It'll probably be sore if that ever happened. Luckily, we never had that happen.
That's amazing. I did not realize that you jettisoned that. Is that the word, jettison?
Mm-hmm.
I didn't realize you jettisoned that while the second stage was burning.
Yeah, just after second stage gets up burning, then you get rid of it. Now the instrument unit, we talked about it, this is where it's located on top of the third stage. Okay, now, when we get to this point, we will just, the lunar module is inside the tapered section up here. We've jettisoned that launch escape tower, so it's no longer there. The command module and the service module are going to stay together until just before they re-enter the Earth's atmosphere coming home. So at this point now, they're heading toward the moon. We're probably 600 or 800 miles above the Earth, not very far yet. Still got about 3 days to get to the moon. So the crew now, the command modules, service modules together, they will separate from the SLA, the spacecraft lunar module adapter. They will separate and move away from the rocket, and then they'll turn around. Okay. As they're turning around, we'll jettison 4 panels on this SLA here, which is part of the instrument unit control stuff again. Center command will jettison these 4 panels. That leaves the lunar module still attached to this lower part of the SLA with the top end of the lunar module pointing forward. The command module goes out, turns around, comes back and docks with the top part of the lunar module. They dock and then they will hook up some cables and some latches. Then they throw a switch in the command module and that releases the lunar module from the rocket. Now they're going on their way to the moon. Now the moon's up here, they're down here 3 days away almost. The spacecraft, moon's moving like so, they will follow a trajectory and go around the leading edge of the moon. Fire that service module engine, slow them down, put them in orbit, do their thing, and then they use the service module to get away. When we shut down the stage, we're going 24,500 miles an hour. We're only a few hundred miles above the Earth. So Earth's gravity is slowing them down very quick. By the time the crew separates, everything is probably slowed down to maybe 12, 14,000 miles an hour, because you're still very close to the Earth. So Earth's gravity is saying, come on back home, guys. So this thing now, when they separate, they would slow this stage down maybe 7 miles an hour, 8 miles an hour. They would speed up the spacecraft a few miles an hour. And the reason is so much momentum with this. If we did not slow this stage down, there was a very high probability that before they could reach the moon, the S4B stage would run into the spacecraft.
Oh.
Okay. So this was a safety.
So they may be flying in formation, and you don't want that.
Well, you're going. I mean, you're going to the same place if you don't do something. So we would make that was a safety measure.
How would you fire? Where would the rockets at?
That's that auxiliary propulsion system back there.
The little black thing right there. Okay.
Once we had done that maneuver, okay, and everything was okay. Now, depending on the mission, the early missions, what we would do then is we would actually reorient the stage, pump some propellant out the back of it that's left, a little bit of propellant left. Don't fire the engine, just pump it out of it. Fire some thrusters, and the moon's up here, so we'll slow it. Let's say we're going 12,000 miles an hour. We slow this thing 85 miles an hour out of 12,000. It will go around the trailing edge of the moon.
Really?
We get within 2,000 miles of the moon's gravity now, throw this in orbit around the sun. So we got 5 of these orbiting the sun.
Right now?
Right now. Now, beginning with Apollo 12, the astronauts would leave instrument packages on the moon called Apollo Lunar Surface Experiment Package, ALSEP. One of the science objectives of Apollo was to determine what the interior of the moon, what's the consistency. Does it have a molten core like the Earth? Is it sort of like a consistent density, or does it have mass concentrations, which it turns out it does. So beginning with Apollo 13, after 12, and every time they land, they leave an ALSEP package. So at Apollo 13, instead of slowing at 85 miles an hour, we'd slow at 45 and slam it into the moon. This thing hitting the moon is about somewhere around 10 to 11 tons of TNT.
What?
Create about a 2.5 to 3 hour moonquake. It rattled it pretty good. All the little green men are running around. Oh man, the Americans are back.
It would be a moonquake, wouldn't it?
Yes,
it's not an earthquake.
Yes,
it's
that's right, a moonquake.
And so the computers that you controlled to fire that package, the APS right there. So this computer would control that APS,
right?
And instead of 85 miles an hour deceleration, you'd give it, what'd you say, 45?
Mm-hmm. Yeah, just how many seconds do I burn them?
And so there was a conversation. Hey, computer team, we need you to fire this much so we can slam this into the moon.
Yeah, these were all pre-programmed and pre-planned.
So this is a little loud because of the air conditioning unit back there, but this is what you worked on.
Yes. This instrument unit sits on top of the third stage. Basically, the thing is set up like this so that you can distribute your weight around the outside of the thing and control your center of gravity and so forth, you know. The hope was that we would go on with an Apollo application program, and with this layout like this, with the different thermal conducting panels, we could move equipment around and, you know, do different experiments.
So this thing sat on top of the third stage.
Top of the third stage.
And controlled the whole rocket.
That's right. Those lines up at the top up there you see going down, those were the lines that went down, connect to the other stages to allow us to communicate with them.
That's awesome.
And there were methods in the system for separation to disconnect the cables.
And we made another video about the computer over there. That's a whole different thing, isn't it? Yeah. So I guess if you want to learn more about the computer for Saturn V, you should just go watch that video, I guess. So when you look at this thing right here, so this is the computer, the instrumentation ring, right?
Yeah.
What do you feel when you see this?
What do I feel?
Yeah. Nothing?
Yeah, I've been there before. Yeah. Yeah, well, it's you know, it brings back a lot of good memories, I know that, because this was, so many of us that came in to work on this program were right out of college. So this is something that nobody had ever done before, and it was a great learning experience because there's so many different aspects to it. You know, technology goes from, you know, the RF technology to transmit the data to the ground, the telemetry systems and so forth, the environmental control system.
So did you feel like a pioneer?
I just felt like somebody who didn't know what the heck was going on. I finished college in 1965, okay? I had zero computer courses of any kind, no digital anything. It was all analog. In fact, all my stuff was like TVA power, you know, high big power stuff. So I came here and had to learn a whole nother world. But this is a point that, in my mind, is kind of sad that it hasn't been promoted more. When this program was at its peak, there were 300,000 contractors and 47,000 NASA employees working on this thing. Well, a lot of us contractors had come from college, and we had come into a lot of young folks working on these programs. The things that we learned in this, then we moved, you know, after these programs phased down, most of us went off to other fields. So I started with this and doing flight evaluation and so forth, and, you know, systems and component issues, trying to work through what happened. Then this all ended. We did the computer and the control system for Skylab, worked on that. We had a 24-hour, 7-day-a-week mission support tied in with Houston from our facility here in Huntsville. And then this all really phased down. NASA was getting budget cuts and not really sure where to go with shuttle. So a lot of us went to other things, okay? I worked on a Patriot missile program for several years, and then IBM closed here, and we went to North Carolina in the commercial side of IBM, applying what I learned, a lot of what I learned here. Then they decided, well, we need some engineers that can know some computer science, so they sent us back to get a computer science degree. So my last job at IBM was I was writing software to read handwritten amounts off personal checks.
Really?
That was the first, probably one of the first widespread commercial applications of machine learning that was ever done. That was terrific. Fun job.
So you went from some of the first transistors ever,
Right.
to machine learning,
Yeah.
in your career.
Yep.
What's that like?
That's pretty neat. And then I retired from IBM after 31 years, moved back to Huntsville, spent another 19 years working on Patriot again.
Wow.
So I had a 51-year career.
That's amazing.
Yeah. Let's talk about one more thing here where we talked about when the crew separated, went on their way, then we slowed this stage down and targeted the moon and tried to throw it in orbit. Let's go to Apollo 12. Apollo 12 was absolutely an engineer's dream. There were more crazy things happened on that one than you can imagine. We're trying to send this thing 2,000 miles past the trailing edge to get thrown into solar orbit. On Apollo 12, the tracking system was such that they thought they were going faster than they actually were. So they slowed it down another 25 miles an hour beyond what was already programmed. Well, turns out we missed the moon several thousand miles. It goes into very, very high orbit about the Earth, something like a 70,000 mile by maybe 500,000 miles, something. It's really is very high orbit. Well, over the next several years, this thing apparently, as it's going in this orbit, is getting affected by the Earth's gravity and the moon's gravity, so the orbit slowly gets stretched. Well, there's a point called Lagrange L1 point where the gravity of the the gravity of the sun and the gravity of the Earth equal. Earth's pulling this way the same amount as the sun's pulling that way. Well, the people at, I believe it's JPL, they believe that this thing's orbit stretched out to the point that it went beyond the L1 point and was ultimately pulled into orbit around the sun after all. So this thing goes out there and he orbits the sun. Of course, everybody said, oh, well, we knew that would happen. All right. Everybody believed that. So about 30 years later, 2002, amateur astronomer sees this white dot, goes on the internet, reports that he thinks this is an asteroid, whatever. JPL and I think MIT people start looking at it and scratching their heads. No, the trajectory can't be an asteroid. And I believe it's this Dr. Paul Chodas at JPL. Their group started looking at it, and they are the people who track space junk.
Yep.
And he said that he had done some back figuring and thought this was actually the third stage from Apollo 12, and it was coming back into orbit around the Earth.
In 2002?
2002.
Wow.
So this Lagrange point follows the Earth around the sun, okay? This thing had gotten into some orbit about the sun, and it's just, it's just going to stay in that same pretty well orbit. It may precess a little bit, for the most part. So this Lagrange point now is following the Earth. Well, at this point in time, S4B, the Earth, and the Lagrange point just happen to be at the right point, and this thing gets S4B, and the instrument unit gets pulled back into orbit around the Earth. So it orbits the Earth for about a year, gets near the moon on one of these orbits, and gets thrown back into solar orbit again. Now, the people at JPL said they think this is going to happen again, will re-happen about every 40 years for the next 1,000 or 2,000. Ultimately, it'll run into the Earth or the moon.
And that's all because this little module right here, the APS on the back of the third stage, fired just a little bit.
25 miles per hour too much, yeah.
And that put this thing in.
Started all this foolishness, right. So
This started all this foolishness.
yeah, right. So this guy is still floating around. If you want to know about it, you can go out on the internet and do an internet search on J002E3. That's the space junk number for this thing. And there's a couple of people have put plots of what the JPL simulation is that shows this thing coming around L1, orbiting the Earth, and you can see every time it gets close to Earth, you can see how the shape of the orbit changes. And then on this last one, it comes around and the moon just grabs it and throws it out into orbit.
But my grandkids will see it again.
I could.
That's amazing. That's awesome.
Some poor slob 2,000 years from now going to be walking down the street, see this shadow getting big, real quick. Smack. I wonder what that was.
That's amazing. All right, Luke, you've talked a lot about the rocket, all 3 stages, the instrumentation ring here, and then we get up to this business up here. I notice you don't talk a lot about this side over here.
Well, yeah. Well, we were the rocket guys. That was our part.
You were like a tractor.
Yeah, that's right.
You hauled them up there.
That's right.
And then so Johnson would handle most of this.
Yeah, well, the Johnson Space, from the instrument unit forward, is all Johnson Space Center. They're responsible for all of that.
So your job was done in how much time once, from T0 to how long?
Well, the instrument unit would last about 11 to 12 hours. The batteries would run down. So after that, we couldn't do anything else. That was our part. We got them on their way, and we got this thing heading either in solar orbit or we're going to crash it into the moon, one of the two. And then that was, the launch vehicle pretty well done all it can do.
So what did it feel like when you saw Neil Armstrong step out of the spacecraft?
Yeah, pretty cool. I think the biggest problem was my daughter was sitting in front of the TV and I couldn't see.
Really?
Hey, Carmen, move over a little bit. And that was, I think we all kind of just, wow, can't believe this.
And you were part of it.
Oh yeah, had a little piece of it.
I hope you enjoyed this video. It's something I wanted to make. I love Luke. I just wanted to hear it straight from the horse's mouth. Luke's an amazing guy, and just hearing him talk, I could do it forever. In fact, I recorded about almost 3 hours worth of footage, and I made a big, long version of this interview over on the second channel. If you want to check that out, Smarter Every Day 2. Also, I want to say this. I want to say that Luke made a special effort to tell me about his amazing wife, Kitty. Kitty recently passed away, and Luke just wanted me to let you know that she was a big driving force into enabling him to do what he does, as my wife Tara is to me. So just a huge thank you to Kitty Talley, who wasn't able to watch this video, but she's a very special person, and I would be remiss if I did not give her credit in Luke's life, as well as the men and women that made the Apollo program happen. There's over 350,000 people that did this. Luke also wanted me to say he wasn't the only guy that did Apollo, but I think that's clear. But Luke's humble, and it was important for me to say that. Thank you so much to everybody that supports Smarter Every Day on Patreon. Right now, YouTube's not really, it's not a place where you make big, long videos like this, but I think it's important to do this kind of stuff. So thank you to everybody that supports on Patreon at patreon.com/smartereveryday. That's a goodwill engine, and I really appreciate it. So thank you so much. Feel free to subscribe if you're into this sort of thing. If not, no big deal. I'm Destin. You're getting smarter every day. Check out that big, long video on the second channel. Have a good one. Bye.